In this video, we are going to solve one practice numerical problem based on LC oscillations. So let us first read the problem, and we are going to read the problem keeping in mind that we have to list what is given, what is asked, and at the end, formula used. Let us read it first. A 20 microfarad capacitor is charged by a 150 volt power supply, then disconnected from the power and connected in series with a 0.280 millihenry inductor. The given quantities are C is given as 20 microfarad, voltage is given as 150 volts, later connected in series to an inductor, so L is given as 0.280 millihenry. Calculate A, the oscillation frequency of the circuit. So we are asked to calculate F. Then B part, we are asked to calculate energy stored in the capacitor. UC is asked. At T equal to 0. And then C part is energy stored in the inductor at 1.3 milliseconds. So energy of the inductor at T equal to 1.3 milliseconds. What is the equation that we are going to make use of? First, in A part, we will be using oscillation frequency equation, where we know omega, which is equal to 2 pi f, which is given by, for oscillatory tank circuit, it is given by 1 upon L into C. It will make our f to be 1 upon 2 pi into 1 upon root of LC. In B part, we are asked to calculate energy stored in the capacitor at time t equal to 0. Capacitor energy is given by 1 by 2 CV square. This also we know. And in the C part, we are asked to calculate the energy stored in the inductor at time t equal to 1.3 milliseconds. Now, for inductor, we know the charge is given by Q cos of omega t plus phi, where this phi depends on initial conditions. Because we are starting with at time equal to t equal to 0, the moment of connection with the inductor. That means at time t equal to 0, there is no current in the circuit. So at t equal to 0, here, because you can see that capacitor was firstly charged, then disconnected and connected in series to the inductor. So at time t equal to 0, our charge is 0, and hence phi is also 0, because this phi depends upon our initial conditions. So we know that I is dq by dt. Hence, I will become minus omega q sine of omega t. Here, I have also done the substitution of phi equals to 0. So these three are our required equations for calculation of part A, B, and C. So now what is left is just to substitute and calculate. Let's do it one by one. A, frequency. So F is 1 upon 2 pi 1 upon L into C, which is equal to 1 by 2 pi into 1 by L is 0.280 milli and C is 20 micro. 0.280 milli, that makes it 10 to the power minus 3 multiplied to 20 micro. So 20 into 10 to the power minus 6 to the power 1 by 2. Write this also 2 into 3.14 into 1 upon, let us multiply this 20 to 48. Let us multiply this 20 to 0.28. 5.6 into 10 to the power minus 9 to the power 1 by 2. I can rewrite this as 6.28 into 1 upon 56 into 10 to the power minus 10 to the power 1 by 2. Solving it, we will get root of 56 is 7.8. So 1 by 6.28 into 7.48. And this will become 5, which will go up into 10 to the power plus 2.13 kilohertz, which is the frequency. This is our answer for A part. Let us go to B part now. Second is the energy stored in the capacitor at time t equal to 0 milliseconds. So we know the equation also, 1 by 2 CV square. Let's substitute energy in capacitor 1 by 2 CV square at t equal to 0 millisecond. We know the value of C and V, so 1 by 2 into our C is 20 micro. So 20 into 10 to the power minus 6 multiplied to voltage is 150 whole square. This will give us 0.225 joules. Writing unit for every numerical solved is very important. Always write unit next to the answer that you get. Now the third part, energy stored in the inductor at t equal to 1.3 millisecond. We have current equation which we have already converted in the form of omega and t. This omega we will calculate by multiplying f to the 2 pi. So let us do that. And also we will need q. This we haven't written here, so let us write. I missed writing q also. So q is given by C into V. We have the value of C as well as V. So first we will calculate this and then we will substitute in this equation. Current at t equal to 1.3 milliseconds. So we have our equation I equal to minus omega q sine of omega t. Let us write this again in the form of our quantities. Omega equal to 2 pi f and q equal to c into v. Let us calculate this omega and q first and the term inside the sign bracket. That will make our life easy. So q is c into v, 20 into 10 to the power minus 6 multiplied to 1, which will come out to be 3 into 10 to the power minus 3. It's a charge, so coulomb. And omega is 2 pi f, so 2 into 3.14 into our frequency was 2.13 kilo. 2.13 kilohertz. So this omega will come out to be 1.336 into 10 to the power 4 radians per second, because it's angular frequency. For value inside the bracket of sine, it will be easier if we write this in terms of degrees instead of radian. Like here if you see, The answer of omega that we have got is in radians per second. So let us rewrite it. This omega t, this can be written as 2 pi f into t. And in order to convert degree to radian, we can write this omega t is in radian. If we want to convert this from radian to degree, what we do is multiply by 180 and divide it by pi. So I can write this in terms of degree as 180 by pi. That way we can cancel this out. And rewriting omega t in the form of degree, it will become 2 into frequency, which was 2.13 into 10 to the power 3 multiplied to 1.3 millisecond multiplied to 180. This will give us omega t in the form of degree. Here also these two quantities will get cancelled out. This comes up to be 996.84 degrees. Now we will substitute this. Coming back to I is omega, which we calculated as 1.336 into 10 to the power 4 into sine of 996.84 degree. So here this will be minus 40.08 multiplied to minus 0.992, which will come out to be 39.92 amps. This is our I. We are not done yet. Now we want energy in the inductor, which is given by 1 by 2 Li square. That will be 1 by 2 into L is 0.280 millihenry into 39.92 whole square. This will come out to be 0.223 and unit will be joules. This is our answer number C. Thank you.